Your dryer does not need 124 volts to dry clothes. Your dishwasher does not need it to heat water. Your television does not need it to display a picture. Nothing in your house needs it. But your utility delivers it anyway because the meter reads higher when they do. The British solved this with an $80 box that cuts every bill 12%. By the end of this video, you will discover why American power companies buried this and how to do it yourself. Hi, I am Oliver, and welcome to Off-Grid Ohms. Subscribe and hit the bell for more uncovering electrical secrets. The American National Standards Institute publishes a document called C84.1. It is the voltage Bible for every utility in the country. It says your wall outlet should deliver between 114 and 126 volts. That is a 12-volt window, and utilities deliberately aim for the top of it. The reason is simple. If voltage drops too low, you get a brownout, lights dim, motors stall, customers call and complain. But if voltage runs too high, nobody notices. Your appliances just quietly consume more power. Your meter spins a little faster, your bill creeps up a few dollars every month. The utility avoids complaints, you absorb the cost. Now here's the physics that makes this expensive. It comes from a man named Georg Ohm, who published his law in 1827 in Bavaria. Power equals voltage squared divided by resistance. That squared is the part they hope you never learn. It means power consumption does not rise in a straight line with voltage. It rises on a curve. A 5% increase in voltage does not cost you 5% more on every resistive load in your house. It costs you roughly 10% more. The British wiring regulations known as BS 7671 spell this out plainly. Any appliance with a fixed resistance operating at a constant voltage above its design rating will consume more energy and suffer a shortened working life of up to 46%. That is not a typo. 46% shorter life on your light bulbs, your heating elements, your motors. Every excess volt shortens the clock. Think about what is plugged into your walls right now: the heating element in your water heater, the compressor in your refrigerator, the blower motor in your furnace, the pump in your well. Every single one of those devices is pulling more watts than it was designed to use. Not because it needs to, because the utility finds it easier to push too much than too little. You pay the difference in higher bills and shorter appliance lives. Nobody told you it was happening. That overvoltage did not happen by accident. It was baked into the American grid before your grandfather was born. And it starts with a man standing in Lower Manhattan who picked a number off a dynamo in 1882. On September 4th, 1882, Thomas Edison stood inside the Pearl Street generating station and threw a switch. Electricity flowed to 59 customers in Lower Manhattan. The voltage was 110. But Edison did not arrive at that number through careful engineering optimization. He originally planned his entire system around 100 volts direct current. The bump to 110 was a field fix to compensate for voltage drop across his copper distribution lines. The number that would define American electricity for the next century and a half was a workaround, nothing more. What followed was the War of the Currents. Edison championed direct current. George Westinghouse backed alternating current with transformer technology developed by Nikola Tesla. Through the late 1880s and early 1890s, the two systems fought for dominance across laboratories, city streets, and the halls of government. Alternating current won because transformers could step voltage up for long-distance transmission and back down for home delivery. But when alternating current won, it inherited Edison's endpoint voltage. The light bulbs were already built for 110. The sockets were already wired. The factories were already tooled. The infrastructure was locked. Over the following decades, that number crept upward. 110 became 112, then 115, then 117. Finally, in 1967, the standard landed at 120 volts at 60 hertz. Each bump was a quiet adjustment to accommodate longer distribution lines and heavier loads. No one voted on it. No homeowner was consulted. The number just drifted upward because it was easier for the grid. Meanwhile, across the Atlantic, something very different happened. When Germany electrified in the early 1900s, metal filament lamps could handle higher voltages. Without an installed base of low-voltage bulbs to protect, the Germans built their grid at 220 volts. That standard spread across Europe and eventually settled at 230 volts. Europe adopted that higher standard over time. The reason America still runs on 120 volts is not that it is better. It is not safer. It is not more efficient. It is simply what Edison bolted into place in 1882. Once an electrical system reaches national scale, the cost of changing it becomes greater than the cost of living with it. So America kept Edison's number, and every utility in the country kept pushing it 5% higher than your appliances need. Edison's choice became the status quo. The British inherited a grid running at 240 volts. Europe unified at 230 volts. Both sides overshot. But here the story split apart. The British looked at the gap between what the grid delivers and what appliances actually need. And instead of shrugging, they built a fix. Walk into a terraced house in Manchester or a bungalow outside Bristol and open the utility cupboard. Between the electricity meter and the consumer unit, you will find a small box about the size of a toaster. That box is a voltage optimizer. It has been standard practice in British homes for over a decade. It does exactly one thing. It steps the incoming voltage down to what appliances were designed to use. The story behind it starts in 1988, when European nations agreed to harmonize their voltages to a common standard of 230 volts. The agreement formally took effect in 2003, but the United Kingdom never actually lowered its grid voltage. The supply kept running at an average of 242 volts. 30 years after that harmonization agreement, the UK still delivers roughly 12 volts more than the European standard. They changed the label on the paperwork. They did not change the electricity coming through the lines. British engineers saw the gap and created a market around closing it. A voltage optimizer is a series-connected transformer installed between the meter and the consumer unit. Everything downstream receives reduced voltage. Every circuit in the house benefits. Every appliance runs closer to its design point. The documented results are not theoretical. PowerDown 220, one of the largest UK suppliers, reports that customers save 7 to 12% on electricity costs. The British Electrotechnical and Allied Manufacturers Association published findings showing average energy savings of around 13% when supply voltages are reduced to the lower end of the statutory range. In 2023, an independent case study on a home fitted with an Energy Ace voltage optimizer recorded 17% reduction in the first full year. That went beyond the 10 to 15% range manufacturers typically claim. The home saved 2,760 kilowatt hours at average UK rates that translated to over 770 pounds saved in a single year. The payback period runs 2 to 4 years. The expected lifespan exceeds 30 years of trouble-free operation. No moving parts, no firmware updates, no monthly subscription. A box that sits in the cupboard and quietly saves money for 3 decades. Hundreds of thousands of these units are installed across the United Kingdom today, sold openly, installed by licensed electricians in about an hour, 2 wires in, 2 wires out. The technology is so simple, it borders on embarrassing. Which raises a question that should make you uncomfortable. If a 12-volt reduction saves British homeowners 7 to 17% on every bill, and the same physics applies at 120 volts, then why does no equivalent market exist in America? The answer is worse than you think, because American utilities already know voltage reduction works. They have been doing it themselves quietly at the grid level for decades. They just never told you about it. Deep inside utility control rooms across America, operators sit in front of screens displaying real-time voltage data from every substation and feeder line on their network. And when demand peaks on a brutal August afternoon, They do something interesting. They reduce the voltage. The practice is called conservation voltage reduction. The United States Department of Energy defines it as the intentional operation of the transmission and distribution system to provide customer voltages in the lower end of the acceptable range with the goal of achieving energy and demand reductions. Read that definition again. The goal is energy reduction for the utility. Commonwealth Edison serves 4 million customers across northern Illinois. Under the Illinois Future Energy Jobs Act, they rolled out a massive voltage optimization program across their grid. Technicians at substations and engineers in control centers tuned voltage levels on every feeder. The results cut fuel consumption and lowered peak generation demand. The utility captured those savings on their own balance sheets. Here is the part that should bother you. Other energy reduction programs need to attract and enroll customers to change their behavior. Conservation, voltage reduction does not. Utilities roll it out without customer participation, without customer notification, without customer consent. The voltage drops. The meter slows slightly. The utility burns less fuel and pockets the efficiency gain at the generation level before it ever reaches your panel. Your bill stays the same or close to it. You do not even know it happened. The technology is not banned. It is not illegal. It is simply invisible to the code. There is no approval pathway, no inspection checklist, no installation standard written for it. Building inspectors cannot approve what their training never covered. Contractors cannot recommend what their licensing exams never mentioned. The same pattern that buried passive cooling and earth tube systems buried this too. Not prohibition, erasure. Now here is where honesty matters and where off-grid ohms with Oliver parts ways with channels that overclaim. Not every load in your house responds the same way to voltage reduction. Modern electronics use something called a switched mode power supply. Your laptop charger, your phone charger, your smart television, your LED driver circuits, these devices are designed to accept a wide range of input voltage and deliver a fixed output regardless of what comes in from the wall. Reducing voltage to these loads saves you nothing. They draw what they draw no matter what. But the loads that do respond are the biggest energy consumers in the house. Older induction motors in refrigerators and freezers, compressor motors in air conditioning units that predate variable speed drives, heating elements in water heaters and baseboard units on manual switches, incandescent and halogen bulbs still burning in garages, basements, porches, and workshops across America. Well, pumps, pool pumps, attic fans, these resistive and inductive loads are voltage dependent. Push more voltage into them and they pull more watts, whether those watts do useful work or not. A house with an older load profile can realistically expect savings of 10 to 12%. A house full of modern smart appliances with efficient heat pumps and LED lighting everywhere might save 3 to 4%. Still real money over 30 years, but know your load profile before you invest $1. The materials cost for a residential unit runs $80 to $200 depending on amperage and configuration. Before you touch anything, measure first. Get a true RMS multimeter and monitor your incoming voltage at the main panel over a full 24-hour cycle. Document the high reading, the low reading, and the average. Most American homes will consistently read between 122 and 126 volts. A 10-volt reduction brings that down to 112 to 116 volts. The device has no moving parts, no circuit boards, no software. It is copper wire wound around a laminated steel core inside a metal box. It is the same transformer technology George Westinghouse used when he built his first units in the 1880s. It does not wear out the way a compressor does. It does not need refrigerant charges or annual service visits. It sits in the panel and does math with magnetism. That is all a transformer has ever done. Water heaters with thermostats deserve special attention. Reduce voltage to the heating element and it runs longer to reach the set temperature. It uses less power per minute but runs more minutes to complete the same job. Net energy consumption stays roughly the same. The savings on thermostat-controlled resistive loads are minimal, but an unregulated resistive load, like a baseboard heater on a manual switch or a heat lamp in the bathroom, saves real watts immediately. Water heaters behave differently than simple always-on resistive loads. The permit question matters. This is a modification to your service entrance equipment. It handles your full service amperage. This is not a weekend project you tackle with wire strippers and a YouTube tutorial. Hire a licensed electrician. Pull a permit where your jurisdiction requires one. Do it correctly or do not do it at all. The transformer itself is simple. The installation context is serious. Permit and code compliance protect you. Measure your incoming voltage first. If your utility is already delivering 118 to 120 volts consistently, your optimization margin is slim and may not justify the cost. The payoff is largest for homes receiving 124 volts or above around the clock. Most American homes do, but verify with a multimeter and 24 hours of data before you commit. Knowledge costs $20. Assumptions cost more. Verify your numbers. One more thing worth saying plainly. Voltage optimization is not a substitute for real efficiency upgrades. If your attic has 3 inches of insulation from 1972 and your windows are single pane rattling in the frames, fix those first. Insulate, air seal, upgrade the obvious failures. Voltage optimization is the last 12% after you have done the fundamentals. It is not a magic box. It is physics applied correctly at the panel. The physics was settled before Edison ever picked his number. Georg Ohm published his law in Bavaria in 1827. Michael Faraday demonstrated electromagnetic induction in London in 1831. A transformer steps voltage down. Power scales with voltage squared divided by resistance. These are not opinions. These are not trends. These are laws of the physical universe that predate the utility industry by half a century. Physics explains why this works. The British saw the problem. Engineers in Manchester and Birmingham and London measured the gap between what the grid delivered and what appliances needed, and they built a market around closing it. Hundreds of thousands of homes across the United Kingdom already have the fix installed in their utility cupboards right now. Americans have the same overvoltage problem, the same physics, and the same potential savings, and no market, because nobody profits when you use less. United Kingdom engineers acted on that insight. A transformer does not need firmware updates. It does not send monthly bills. It does not break down after 10 years so you can buy the next model. It sits in the panel quietly reducing every watt to what your appliances were actually designed to consume. Simple, passive technology delivers those savings, the same way it has worked since George Westinghouse wound his first coils in 1886. The utilities know this works. The engineers know. The Department of Energy published the data. The code writers left it out. The manufacturers hoped you would never ask. Now you know. Ohm's law works the same in your garage as it does in a British utility cupboard. The voltage your utility has been pushing into your house every hour of every day for years is higher than it needs to be. It always has been. The only question left is what you are going to do about it. If this changed how you think about electricity, please subscribe to Off-Grid Ohms with Oliver. Please watch the next video appearing on your screen right now.